Good day, everyone. So today I am with Miss Acel Carreon and Mr. Crizaldy Francisco, and we will be discussing about contact metasomatic deposits. So first, for our table of contents, in here we have introduction, characteristics of the mineral deposits, types of occurrences, orgenesis, deposits of ore, and conclusion. So for our introduction, we will have the definition of contact metasomatism, and definition of hydrothermal deposits. So first, for metasomatism, it refers to the process whereby a pre-existing igneous, sedimentary, or metamorphic rocks undergo compositional and mineralogical transformations that is associated with chemical reactions triggered by reaction of fluids. Then for our contact metasomatism, um, it is a process wherein there is a formation of new minerals by the reaction between the contact rock and escaping high temperature gaseous emanation with other important materials from the magma chamber. Then lastly, for the hydrothermal deposits, it refers to the accumulation of minerals in fractures and cavities that results to circulation of hot waters in the Earth's crust. And then hydrothermal deposits are mineral deposits that are formed from the precipitation of minerals dissolved in hot water that circulate through rocks. And then in here we have the different types of hydrothermal deposits, which will be also tackled deeper later. So here we have vein deposits, skarn deposits, replacement deposits, epithermal, porphyry, volcanic, massive, sulfide. So for the deposits, these are mineral deposits that occur in fissures or cracks in rocks. So they are formed when hydrothermal fluids circulate through the rocks and deposit minerals in the cracks. Vein deposits are often rich in metals such as gold, silver, copper, and lead. And then for the skarn deposits are contact metamorphic rocks that form when hydrothermal fluids come into contact with carbonate rocks. And it contain a wide range of minerals including copper, zinc, iron, and tungsten. And then for the replacement deposits, um, these are the deposits formed when hydrothermal fluids replace the minerals in the rocks and they come in contact with. Replacement deposits are often associated with limestone or other carbonate rocks. Next, we have the epithermal deposits. So for epithermal deposits, these are formed at shallow depths and are typically associated with high sulfidation or low sulfidation mineralization. And then next we have porphyry deposits. So these are the deposits that are large, low-grade deposits and are often associated with copper and gold. And then they are formed when large volumes of hydrothermal fluids circulate through a large area of rock. And it alters the rock when the depositing minerals. So lastly, for the type, we have volcanic massive sulfide deposits. So the VMS are associated with underwater volcanic activity, and they form when hot, metal-rich, and hydrothermal fluid mix with cold seawater and precipitate metal sulfides. For the next one, we have the metasomatism process. So what is metasomatism process? So this is the process wherein the chemical composition of a rock is altered by the introduction or removal of chemical components, typically through hydrothermal fluids. And then it leads to the changes in mineral composition and texture. And this alteration can happen at high temperatures and pressure. So, Types of metasomatism. So the types are divided into two, and it depends on the metasomatic process and geologic position. So in here we have the diffusional and the infiltration. For the diffusional metasomatism, it takes place by the diffusion of a solute through a stagnant solution. So these two are for the basis of metasomatic process. So the diffusional takes place by diffusion, and then infiltration metasomatism takes place by the transfer of mineral in solution by infiltrating the host rock. So for the summary of the differences between the two, this is a table that presents it. So for the mechanism, for the diffusional, the element transformed via solid state diffusion without fluid movement. And then for the infiltration, fluid move actively through the rock, transporting dissolved elements. Then for the fluid pathways, for diffusional, it has no pathways. And then for the infiltration, the fluid travels through fractures, vein, or pore spaces. And for the boundary between altered and unaltered rock, for the diffusional metasomatism, we have gradual or diffusion transition, and for the other one, we have sharp and well-defined alteration zones. So next, we have the next basis, which is the geologic position. So for the geologic position, we have three: the contact, regional, and hydrothermal metasomatism. So for the contact metasomatism, it occurs at or near the contact between a magmatic body and other rock. And then for the regional, it occurs over large or great areas, commonly from alkaline metasomatic rock during the magmatic and early post-magmatic stages. Examples are regional metamorphism can lead to the formation of metamorphic rock like schist. Next, we have the hydrothermal metasomatism. This type can be driven by high temperature fluids, often associated with hydrothermal systems that interact with rocks. Next we have is the characteristics of the mineral deposits. So for the characteristics here, we have four. We have high temperature formation, association with igneous intrusions, zonal mineralization patterns, and common mineral assemblages. So for the first one, we have high temperature formation. So it is stated here that mineral deposits form at high temperatures. And the ideal temperature for crystallization of minerals are 300 degrees Celsius to 800 degrees Celsius. And this temperature is ideal because it leads to the formation of specific mineral types often associated with igneous activities. Next we have is the association with igneous intrusions. So for this, the interaction of hydrothermal fluids with igneous intrusions lead to the replacement of wall rocks and formation of characteristic mineral assemblage. This process is a key feature of skarn mineralization. Next we have is the zonal mineralization patterns. So it refers to the occurrence of different mineral types in concentric or banded patterns around central igneous intrusion or hydrothermal system. And this one occurs in distinct zones around the igneous intrusions, and it occurs because of temperature, pressure, and fluid composition change. Next is the common mineral assemblages. So these are the minerals that compose, these minerals compose the present rocks. And the common minerals include garnet, pyroxene, magnetite, and sulfides. So garnet are commonly found in skarn deposit, and particularly in the early stages of its formation. And then for the pyroxene, another common mineral, it is another common mineral in skarn deposits, and often found alongside with garnet. And then for magnetite, it is an iron oxide that can be abundant in skarn deposit as well, and particularly for iron-rich skarns. And then for sulfides, um, um, these are like the chalcopyrite, pyrite, sphalerite that can also be found in skarn deposit, and it is found in later stages of its formation. And those four are the characteristic of mineral deposits. Next part will be discussed by Crizaldy Francisco.
Now, what is an skarn deposit? Skarn deposit a type of metasomatism where a hot pluton was entered in the carbonate rock such as the limestone, and this hot pluton was a magmatic fluid that rich in silica, calcium, magnesium, and iron that can change the chemistry of limestone, that forming a mineral to the skarn deposit such as a garnet, epidote, magnetite, and pyroxene. And as we can see in the image, the hot pluton was entered in the carbonate rock such as the limestone, shale, and dolomite. And we can see also the image the different type of skarn such as the endoskarn and exoskarn. I explain later what is the meaning of exoskarn and endoskarn, but we can classify the type of skarn differs on each differ on their protolith or the rock origin where the metamorphic rock was formed. That is the meaning of protolith. Now, this is the example of skarn deposit from the Mount Monzon in northern Italy. We can see this is a recrystallized calcite, and because of the intrusion of hot fluid or hot pluton in carbonate rock, we can see a mineral such as the garnet and pyroxene, where the color brown is the garnet and the green color naman is the pyroxene. Now, ito yung sasabi kong meaning ng exoskarn and endoskarn. Skarn can be classified according to its protolith or yun nga yung rock origin ng metamorphic rock. Where in the exoskarn, if skarn protolith is sedimentary origin and endoskarn naman is igneous rock. So ang pinagkaiba lang nila, ang exoskarn is from the yung protolith niya is from the sedimentary origin and the endoskarn naman is the igneous rock. Gaya din makikita natin yung shale because of the intrusion of the hot pluton, nagkaroon siya ng exoskarn kasi alam natin ang shale nga is in the sedimentary origin. Well, dito naman magkakaroon ng endoskarn since sa igneous form naman siya mabubuo. Now, skarn also classification can be made based on the protolith of observation of the skarn dominant composition and the resulting alteration assembly. Example, if the skarn has a composition of olivine, serpentine, progopite, magnesium, cyanopyroxene, orthopyroxene, spinel pargasite, and other minerals from the humid group, we can classify it as dolomite from dolomitic protolith. And we know that dolomite is rich in magnesium, so it can be classified as in magnesian skarn. Now, we know that in every deposit or ore, there are a ganj mineral. Siyempre, ang skarn deposit, meron din siyang mga ganj mineral, but it can also contain ore minerals that can help in our economic importance such as the copper, iron, and other mineral. There are different type of skarn deposit. The iron skarn, gold skarn, tungsten skarn, copper skarn, zinc skarn, molybdenum skarn, and the tin skarn. Now, what is this iron skarn? Iron skarn is the largest skarn deposit kumpara sa iba't ibang skarn. And there are economical value because of their magnetite composition. And we can also find a small amount of nickel, copper, cobalt, and gold. But only minor amount lang na makikita natin sa iron skarn. But typically, ang mga nire-recover, ang ginagamit sa commonly sa economical value is yung nire-recover na iron. Because nga is the iron skarn is dominantly magnetite. And yung mga ganj or lang niya ay yung mga silicate. Next, what is the gold skarn? Gold skarn naman is parang Nabubuo siya because of the mafic diorite or granodiorite pluton and dike or sill complex. And some iron and copper skarn have also a gold in the distal zone. Next, what is the tungsten skarn? These are found in association with alkaline pluton in major orogenic belt, and they are associated with coarse grain, equiglanar batholite with pegmatite and uplite dikes surrounded by hot temperature metamorphic oroliths. This is indicated in deep environment. Next, copper skarn. These are the world's most abundant type and particular common in orogenic related to subduction both in continental and oceanic setting. You know na kapag nagkakaroon ng subduction, mas makita natin dahil sa subduction ng ng continental and oceanic, yung mga magma natin ay nag-rise pataas sa earth surface, kaya commonly nagkakaroon ng mga different type ng skarn, and especially na doon na nabubuo yung mga copper skarn and mga zinc skarn. Yun nga, yung sa zinc skarn, ganun din, parang nabubuo siya because of the subduction and drifting. Kasi nga parang mas mabilis umangat yung mga magma rising, which is dahil sa pag-angat nga ng mga hot pluton, nagkakaroon ng nag-i-intrude sila sa mga carbonate rocks and nagpo-form ng skarn deposit. Next, the molybdenum skarn. Most are associated with leiocratic or the lacking of ferromagnesian minerals. Granite can form high-grade small deposit. Other metals are also commonly associated, the most common being MoWCO skarn. Now, what is the tin skarn? These are the almost exclusive associated with high silica granites generated by partial melting of continental crust. Recent alteration by fluorine produce a characteristic yellowish mica. Now, ano naman ang resin deposit? Yung kanina ang skarn deposit is yung hot pluton ay nag-i-intrude sa mga carbonate rock. Now, the resin deposit naman ay in the granitic rock. It is a parang sa mga granitic rock naman siya mga nag-i-intrude or sa mga veins na rin. Now, resin is a hydrothermally metamorphosed granitic rock usually composed predominantly of quartz and mica. Tas ayun nga, yung resin is typically mga nag-o-occur sa mga belts or vein ng mga granite that nag-intersect siya doon para parang pumapasok siya doon sa mga gitna or sa mga veins ng mga granite. And the transaction between two rocks is gradual, indicating that the resin had been produced through alteration of the granite by vapors of fluid rising through fissures. Yun nga, sa mga fissures sa mga veins. This is an example of resin deposit. Now, what is the pegmatitic contact? Pegmatite is an igneous rock that form end of the stage a magma crystallization. Pegmatites contain a exceptional large crystal and they contain rarely minerals than other types of minerals. Generally, most pegmatites are found in sheets of rock that are dikes and veins, also near large masses of igneous batholiths. Pegmatites also form in small pockets along the margin of batholith, leading a pegmatite stack. It will form from water that separates from a magma in the late stage of crystallization. Now, porphyry deposit. Porphyry deposit are a special kind of hydrothermal deposit kung saan dahil sa mga hydrothermal fluid from the magmas at depth, nagdadala siya o kine-carry niya paangat sa surface yung mga deposit minerals to create or deposit. Makita natin din sa image. Ito yung example ng isang porphyric copper deposit. Ito yung parang hydrothermal fluid itong image na to, and kada depth niya may iba't ibang minerals or metals na dinadala siya. Nakadepende siya sa lalim or sa init ng magma. Like dito sa baba may chlorite, sa epidot, magnetite, sa taas quartz, ganun, and others. In porphyry deposit, formulas are in small veins with a hydrothermal altered host rock. Generally, a porphyritic felsic to intermediate composition intrusive. These deposits are important source of copper, molybdenum, and gold. They may also yield tungsten or tin. Tapos yung image dito is an example of porphyry deposit in Morenci, Arizona. Gaya nga sabi, ang porphyry deposit commonly Parang sa mga small veins din siya dumaan yung mga hydrothermal host rock. Ito naman yung example ng iba't ibang skarn. Like this in the first, ito ay isang iron skarn kung saan makikita natin yung mga magnetite deposit. Ito ay makikita sa Utah Iron Spring Mining District. And next naman is yung gold skarn sa Northern Texada Island. Di lang medyo halata pero kung yung mga ito ay mga gold yan. Gold minerals. And lastly is the tactite skarn or the carbonate. Commonly carbonate lang yung mga yan. And ito naman isang example ng tin tungsten core sa North Cornwall, England. Kung saan makita natin sa grazing or pagpasok, ito isang talaga granite dahil because of the high temperature hydrothermal solution, nag-altered yung host rock niya and nagkaroon ng force and sa vein parang pumasok yung grazing deposit. But the ore contains traces of tin, but tungsten is the principal metal of economical interest. Now, example of skarn deposit around the world. Ito yung mga mga malalaking mining in world po. Number 1 is the Bingham Canyon mine in USA. This is the one of the largest open pit copper mine in the world, located in US sa Utah. Tas primary a copper, gold or molybdenum porphyry deposit, but it also includes skarn mineralization with significant reserve of tungsten. Next naman is the Antamina mine in Peru. Dito naman ay commonly mga large copper, zinc and silver gold skarn deposit ang makikita. Next naman is the Yerington mine in USA. Ganyan din mga copper gold skarn deposit located in Nevada, USA. It was historically an important source of copper but has been inactive for several decades. Next is the Tungsten Queen mine in USA. This is a historic tungsten skarn deposit located in North Carolina, USA. It was an important source of tungsten during World War II. And lastly is the Metasomatic mine in Australia, kung saan ito isang one of the largest tungsten deposit in the world. And madami pa tayong iba't ibang skarn deposit around the world. Ito lang ilan sa mga example. Ito yung isang image o mga image ng mga company mining sa buong mundo makita natin. Like sa Bingham Canyon mine, Antamina mine in Anden sa Peru. Next, factor in contact metasomatic deposit. First is the orgenesis, or we know that orgenesis the process kung saan nagpo-form yung mga ore deposit natin. It involves the study of geological, geochemical, hydrothermal, and other processes that contribute to the formation of mineral deposit, including factors such as temperature, pressure, fluid composition, and geological environment. Siyempre sa pag-form ng mga ore deposit, parang nagiging factor natin yung temperature, pressure, and fluid composition. Sa pag-iba-iba nyon, nagbabago din yung level ng ore deposit natin. In orgenesis, there are three types or three components of orgenesis. First is the source, second is transport, and trapping. In source, it's required because metal must come from somewhere and be liberated by some process. Next, the transport is required first to move the metal-bearing fluid or solid minerals into the right position and refers to the act of physically moving the metal as well as a chemical or physical phenomenon which encourage movement. Next is the trapping. It's required to concentrate the metal via some physical or chemical or geological mechanism into a concentration which form mineable ore. Next naman na factor is yung magmatic or hydrothermal fluid. Kung saan yung magmatic or hydrothermal fluid is from the sa pinakailalim ng basta at the depth ng subsurface natin or sa mga volcanic sa mga baba doon. As the magmatic hydrothermal fluid plays a key role in variety of geological processes, including volcanic eruption and even formation of ore deposit whose metal content is derived from magmas and transported to the site of ore deposit by means of hydrothermal fluid. Yun nga, yung sa magmatic hydrothermal fluid natin, which is because ng mga we know that magma carry the metal, and because of that, we can see, it's transferred, the magma was transported to the ore deposit by the hydrothermal fluid. As the magmatic hydrothermal fluid is formed during the course of magmatic evolution, lobotolysis and CO2 to CH4 rich at primary basaltic magmatic phase to the saline water rich is during granite or pegmatite formation. Large number of constituents, including the common metals and even RRE, may be found in it. Next naman is the fluid-rock interaction and metasomatism. We know that hydrothermal fluids was react different type of surrounding rock, and it will altering the pH and redox condition. Like this process leads to precipitation of metals like iron sulfides or the pyrite, the chalcopyrite and galena. Yun nga, yung fluid rock interaction is yung dahil sa contact nyon sa mga rocks, yung chemical react to achieve a state that approach the dynamic equilibrium. And the fluid rock interaction is an exchange of isotope and or an element taking place at increasing temperature. The interaction involves the dissolution, precipitation, chemical exchange, reaction, redox reaction, diffusion, and their combination. Basta sa fluid rock interaction, din nilang yung parang nangyayari dahil sa pag-interact niya sa rock, nagkakaroon ng mga dissolution or precipitation, chemical exchange, reaction, redox reaction, diffusion, and their combination. Ay lang yung tandaan nyo pagdating sa fluid rock interaction. Next naman is, ano ba yung sa tawag ng metasomatism? Ito yung refers to the process whereby the pre-existing igneous or sedimentary metamorphic rock undergoes composition and mineralogical transform associated with chemical reaction triggered by the reaction of fluid or the metasomatic agent which invade the protolith. It is traditionally defined as metamorphism which involve a change in the chemical composition, including volatile composition. Next na factor is yung thermochemical and pressure influence. Once yung pressure ay bumaba or suddenly drop dahil sa mga faulting or fluid escape, mas bumibilis o nag-rapid yung metal deposition, like ng mga gold bearing quartz veins are nabubuo dahil sa mga condition ito. Tas pag mataas naman yung temperature natin or temperature ng magma, nag-i-increase naman yung nag-i-increase naman po yung metal solubility natin. And as fluid migrates away from the heat source, cooling leads to decreased solubility and or precipitation. Tandaan lang natin, pag bumaba yung pressure, mabilis ang metal deposition, and pag mataas ang temperature, mabilis ang metal solubility. And kapag malayo sa heat source, yung cooling leads ay bumababa ang solubility and or precipitation. Now, reaction with chemically reactive wall rocks usually of reduced oxidation state, such as an iron-bearing rocks, mafic or ultramafic rocks of carbonate rocks. The gassing of the hydrothermal fluid into a gas and water system or boiling, which alter the metal carrying capacity of the solution and even destroy metal carrying chemical complex. Next naman is yung metal transport mechanism or the chloride and sulfate complex. Kung saan naman din sa sodium chloride is the ubiquitous salt is in hydrothermal or solution, and hence the stability of chloride complex many element at high temperature and pressure plays a fundamental role in the transport of this element by migrating or fluid throughout the earth crust and their subsequent precipitation as or minerals in or depositing environmental at given temperature and pressure. Bali, ang pinaka-factor talaga sa mga ganito is yung temperature and pressure.
For the deposition of contact metasomatic deposits, we will be discussing the deposition based on the type of deposits, its structural and chemical controls, the depositional texture, wall rock alteration, gum minerals, pyrogenesis, and zoning. For recap, the deposition is the process by which ore minerals accumulate in a specific geological setting. The structural controls are the geologic structures that influences where the ores are deposited, like faults, fractures, folds, and intrusive contacts that acts as a pathway for hydrothermal fluids directing mineralization into favorable zones. The chemical controls are the factors that determine how minerals precipitate. The depositional texture are those characteristics that describe how ore minerals appear and arrange within the deposit. Wall rock alteration are the alteration that occurs when hot fluids chemically modify the surrounding rock. The gum minerals are the non-economic minerals that form alongside ore minerals. Parogenesis is those that refer to the sequence of mineral formation in the deposit. And lastly, the zoning describes how minerals are spatially distributed in the deposit. To recall the types of deposits that was described earlier, we have the skarn deposits, Grayson deposit, pegmatitic contact deposits, and porphyry-related deposits. First off is the deposition of skarn or deposits, where skarns form at the contact between an intrusive igneous body and carbonate-rich rock like limestones or dolomites due to metasomatic exchange. It is where mineralization occurs as hydrothermal fluids replace the host rock with calcium-rich silicate minerals and ore minerals. And it is found in contact zones of granitic intrusions within carbonate sequences and is commonly found along convergent plate boundaries, particularly on subduction zones. The structural controls of skarn deposits includes faults and fractures, fold hinges, bedding planes, and contact zones, where faults and fractures acts as a major pathway for hydrothermal fluids, allowing the mineralizing solutions to penetrate carbonate host rocks. The fold hinges acts as a trap for ascending mineral fluids. The bedding planes in carbonates enhances the permeability in layered limestones or dolomite, which provides fluid migration pathways, and contact zones, which is the boundary between an igneous intrusion and the carbonate host rock and is the primary location of mineralization. The chemical controls include CO2 and carbonate composition, where skarns develop when acidic hydrothermal fluids interact with carbonate host rocks, where like limestone or dolomite driving decarbonization reactions, where it produces minerals like wollastonite, garnet, and pyroxene. The next chemical control is the silica-rich fluid, where it introduces silicate minerals like garnet and pyroxene into the carbonate rock. The next chemical control is the iron activity, where it controls the formation of magnetite and hematite. And lastly is the sulfur content and redox conditions, where it influences the sulfide depositions. For the depositional texture of skarn deposit, we have granuloblastic to porphyroblastic texture, where granuloblastic texture is the characterized by a mosaic of equidimensional subequalized grains, typical of non-foliated metamorphic rocks, and porphyroblastic texture are those that feature large, well-defined crystals, which we call porphyroblast, within a finer grained matrix. The wall rock alteration of skarn deposits include the prograde skarn alteration, retrograde skarn alteration, and carbonate dissolution and decarbonization, where prograde skarn alteration occurs at high temperature metasomatism at 400 to 800 degrees Celsius, where the development of garnet, pyroxene, and wollastonite occurs. It is where the intensive replacement of limestone or dolomite into calcium-rich silicate occurs. The next alteration is the retrograde skarn alteration, where it occurs at lower temperature of hydrothermal activity, which occurs at less than 400 degrees Celsius, and it is where the formation of epidote, chlorite, and actinolite, amphibole and cerussite occurs. It is where the also where the deposition of sulfide minerals occurs due to cooling fluid. And lastly, the carbonate dissolution and decarbonization uh, is characterized by the loss of CO2 from host limestone, which enhances the permeability, further promoting the metasomatic reactions. The stages of pyrogenesis is the prograde stage and the retrograde stage. The prograde stage occurs at high temperature at approximately 400 to 800 degrees Celsius, where initial thermal metamorphism and metasomatism occur. It is where the formation of high temperature calcium-rich silicate minerals occur and the crystallization of dominant minerals like garnet, pyroxene, and wollastonite. The next stage, or the last stage of pyrogenesis in scar deposit is the retrograde stage or the intermediate to low temperature and occurs at less than 400 degrees Celsius. It is where the hydrothermal overprinting or the replacement of prograde skarn minerals occur. It is where the formation of epidote, chlorite, actinolite, and amphiboles occurs, and the deposition of sulfides like chalcopyrite and sphalerite occurs, and it is also called as the late stage of quartz and carbonate veining. For the zoning of skarn deposits, it is where the mineral composition of the skarn zone changes as you move far away from the contact between the magma and the host rock. And the zoning of skarn deposits are characterized by two types. We have the proximal zone and the distal zone. The proximal zone, meaning near the magma, where these zones are often rich in garnet and pyroxene, and distal zone is those that are further from the magma. This listal zones may contain more carbonate minerals like wollastonite or other pyroxenoids. The factors affecting the zoning of skarn deposits include the magma composition and temperature, where the types and temperature of the magma influences the types of mineral that form. Um, the host rock composition also affects the zoning by the type of carbonate rock that affects the resulting mineral assemblages. The fluid flow also affect the zoning because the path and direction of fluid flow influence the distribution of minerals. And lastly, the temperature, where higher temperature near the magma promote the formation of anhydrous minerals like garnet and pyroxene, while lower temperature favor hydrous minerals. The next deposit is the grayson ore deposits, where these are formed along the upper margins of cupulas. The cupulas are the dome-like structures of granitic intrusions where late-stage hydrothermal fluids enrich the rock in volatile elements. It is located or found within or near the roof zones of evolved granitic plutons, particularly in stable continental settings. Its structural controls includes the cupulas of intrusions, shear zones and joints, and breccia zones. The cupulas of intrusions are the uppermost part of granite intrusions where volatile rich fluids accumulate. The shear zones and joints provide secondary permeability for mineralizing fluids, and breccia zones enhance the fluid circulation through fractured host rocks. The chemical controls include fluorine and boron enrichment, where fluorine-rich fluids promote the formation of topaz, fluorine, and tourmaline. We also have high silica activity, where it leads to quartz muscovite, grayson alteration, and granitic cupulas. Lastly, we have the lithium and tin-rich fluids, where tin and lithium remain soluble in late-stage fluids, leading to the deposition of cassiterite and spodumene. The common depositional textures include the granular texture, which is as discussed earlier, it is the equigranular quartz and muscovite, indicating recrystallization. We also have pseudomorphic texture or the replacement texture, where the chemical or structural change of another substance retain its original external shape. It is the where the primary feldspar is replaced by muscovite, topaz, or fluorite. We also have the veinlet and stockwork texture, where grayson minerals occurs as fine veinlets cutting through the altered granite. Aside from these three, we also have the graphic texture, which is characterized by the intergrowth of quartz and feldspar, forming a distinctive pattern similar to cuneiform or other writing patterns. The Lastly is we have the open space filling texture, which is a hydrothermal alteration of granite, typically feature minerals like quartz, muscovite, and potentially topaz, fluorite, and tourmaline filling in fissures and cavities within the altered granite. For the types of wall rock alteration, we have graysonization, where it is the intense replacement of feldspar by muscovite, quartz, topaz, and fluorides. It requires fluorine and boron enrichment in hydrothermal fluids. Silicification, which is the enrichment of coarse vein due to high silica activity, and the sericitization, where it is the breakdown of feldspar into fine-grade sericite. The stages of paragenesis includes prograde stage and retrograde stage. The prograde stage occurs at approximately 500 to 700 degrees Celsius, where there is a breakdown of feldspar and the formation of quartz muscovite. The graysonization of granite due to the fluorine and boron-rich fluids occurs in prograde stage, and it is where the replacement of feldspar by quartz, muscovite, and topaz occurs. It is also where the formation of tourmaline, fluorite, and cassiterite in tin-bearing system occurs. The next stage of paragenesis is the retrograde stage, which occurs at approximately 200 to 400 degrees Celsius, where the deposition of sulfide and the vein formation occurs. It is where the quartz veins with wolframite, molybdenite, and pyrite occurs, and the deposition of bismuthnite, stannite, and sulfides in fractures. For the zoning of grayson ore deposits, we have the vertical and lateral zoning. Vertical, meaning it occurs vertically with different mineral assemblages forming at different depths or heights within the grayson deposit. On the other hand, the lateral zoning occurs laterally, which with different mineral assemblages forming along the margins or within different parts of the grayson deposits. This zoning can be caused or affected by the fluid chemistry, where the composition of our hydrothermal fluids, including their temperature, pressure, and chemical content, plays a crucial role in controlling the mineral assemblages that form. It is also affected by rock permeability, where the permeability of the host rock and the pathway of fluid flow can influence the distribution of minerals. It is also controlled by reaction enhanced permeability, where the graysonization process itself can enhance permeability, allowing fluids to flow more readily and potentially leading to more complex zoning patterns. And lastly, It is also influenced by magmatic processes where the nature of magmatic systems, including the type of magma and the timing of its crystallization, can influence the zoning patterns. For the deposition of pegmatitic contacts, pegmatites crystallize from last volatile rich portion of a cooling magma and are deposited along fractures or intrusive contacts. Contact pegmatites develop when pegmatitic fluids react with the surrounding host rock. It is found along the margins of granitic intrusions and within shear zones in continental crust, often in shield areas and drift zones. The structural controls includes the faults and shear zones, intrusive margins, dikes, and veins. The fracture and shear zones, it is where pegmatites often intrude, and the intrusive margins form along the contacts of granitic intrusions, and the dikes and veins is where the mineral-rich fluids deposit pegmatite minerals along small intrusive bodies cutting through host rocks. The chemical controls includes the water and volatile rich fluids, where pegmatites form from highly fractionated magmatic fluids containing such minerals influencing mineral deposition. Next is the alkali elements that controls the crystallization of lithium-bearing minerals, and the rare earth elements or the REEs and phosphorus that promotes the formation of REE minerals such as monazite and xenotite. For the depositional textures, we have the graphic texture, which, as discussed earlier, is the intergrowth of quartz and feldspar indicating simultaneous crystallization. We also have the zoned texture where the coarse grained minerals occur in concentric bands that is characterized by the replacement of original granite minerals by quartz, muscovite, and other minerals, and is sometimes with distinct zones of varying mineral compositions. We also have euhedral crystal texture, which is characterized by the large well-formed crystal of beryl, spodumene, or tourmaline due to slow cooling. We also have the perithetic texture, where it is the exsolution of lamellae in feldspar due to cooling and phase separation. And lastly, we have the texture of fracture field texture, where it is characterized or defined by the late-stage mineral deposited in the fracture. The types of wall rock alteration includes albitization, where it is the sodium metasomatism that leads to albite feldspar replacement of host rock minerals and is associated with lithium-rich pegmatites. Next is the phosphatization, where the formation of apatite and monazite due to phosphate-rich pegmatite fluids occurs. And lastly, we have the lithium and boron enrichment, where tourmaline or the boron bearing and spodumene, the lithium bearing, replaces the feldspar or their form in veins. For the stages of paragenesis, we have the magmatic, hydrothermal, and late stage vein formation. The magmatic stage occurs at approximately 600 to 800 degrees Celsius, where the crystallization of feldspar and quartz occur. And the hydrothermal stage occurs at approximately 300 to 500 degrees Celsius, and where the alteration of mineral enrichment occurs. It is where the fluids introduce boron, lithium, and rare metals. Lastly, the late stage formation occurs at less than 300 degrees Celsius, and it is where the alteration of sulfides and secondary alteration occurs, like the deposition of cassiterite, molybdenite, pyrite, and uranium minerals in fractures. For the zoning of pegmatitic deposits, they typically exhibit concentric zoning with mineral variations from the core to the margin due to magmatic differentiation and fluid interactions. The core zone consists of large quartz and feldspar crystals, often with rare minerals like spodumene and beryl, uh, and columbite tantalite. This zone represents the final crystallization stage where incompatible elements concentrate. The next zone is the intermediate zone where it contains coarser grained feldspar, muscovite, or biotite, and other minerals like tourmaline or apatite. It marks as a transition as volatiles deplete and more common rock-forming minerals crystallizes. And lastly, the border zone is a finer grain composed of plagioclase, quartz, and early crystallizing minerals such as garnet, and it is a zone that forms at pegmatite host rock contact, which where it rapidly cools and interact with external fluids. In some cases, pegmatites also develop fluid-driven alteration zones where late-stage hydrothermal fluid introduces secondary minerals like lipidolite or phosphates, which enriches the deposit in rare elements. The zoning in pegmatites is influenced by magma composition, cooling rate, pressure, and fluid activity. For the deposition of porphyry-related deposits, mineralization occurs as hydrothermal fluids from porphyry intrusions migrate into adjacent carbonate-rich country rock, forming skarns and other metasomatic zones. It is common in volcanic arcs above subduction zones, typically in orogenic belts, where porphyry copper, molybdenum, and gold systems develop. Its structural controls include radial and concentric fractures where it is developed around porphyry intrusions, allowing hydrothermal fluids to migrate. The next one is the fault zones, which controls the emplacement of intrusions and fluid pathways, and the brittle to ductile transition zones that controls the location of alteration and mineralization. The chemical controls include the sulfur and oxygen fugacity, where it determines the sulfide mineral deposition and is characterized by two types, which is oxidized condition and reduced conditions, where oxidized conditions favor magnetite and hematite formation, and reduced conditions promote pyrite and chalcopyrite formation. The next one is the chlorine-rich fluids, which enhances metal transport. And lastly, the pH variability, which controls the mineral precipitation, where acidic fluids deposit quartz and cerussite, and neutral fluids to alkaline fluids deposit carbonate gang minerals. The common depositional textures include the stockwork texture, which is a complex system of structurally controlled or randomly oriented veins. And these stockworks are common in many ore deposit types and in gray sands, like what was discussed earlier. They are also referred to as stringer zones. Again, it is a network of thin veins containing quartz, sulfides, and hydrothermal minerals. The next texture is the brecciated texture. In porphyry deposits, breccias generally occurs as steep pipe-like bodies and typically formed at the top of an intrusion, hosting high-grade ore bodies. Hydrothermal brecciation happens due to pressure fluctuations with mineralized fragments cemented by sulfides. The next texture is the disseminated texture where it refers to ore minerals like copper, molybdenum, or gold being scattered throughout the rock mass rather than being concentrated in veins or distinct formations. These are fine-grained sulfide minerals dispersed within the host rocks. Another depositional texture is the veinlet texture, which was discussed earlier. But in this case, it is the chalcopyrite, bornite, and molybdenite that occurs in thin quartz veinlets. And lastly, we have the replacement texture, but in this context, the replacing mineral or the feldspar altered to cerussite and sulfide is replaced by primary silicate minerals. For the types of wall rock alteration, we have the potassic alteration, phyllic alteration, and argillic alteration. The potassic alteration occurs at high temperature greater than 500 degrees Celsius. It is where the formation of potassium-rich minerals such as orthoclase, sanandine, and microcline occurs. It is where the replacement of primary minerals such as plagioclase and biotite with potassium-rich minerals. It is where the formation of K-felds, biotite, and magnetite occurs and is associated with copper molybdenum mineralization. The next alteration is the phyllic alteration, which occurs in intermediate temperature of 200 to 400 degrees Celsius. It is the alteration of primary minerals such as plagioclase, feldspar, and mafic minerals to secondary minerals such as muscovite, kaolinite, and cerisite. It typically involves the removal of most of the original primary minerals and their replacement by secondary minerals. So this is where the major sulfide deposition stage occurs. And lastly, the argillic alteration, which occurs in low temperature, less than 250 degrees Celsius. This is where the formation of clay minerals such as elite and kaolinite form the alteration of primary minerals such as feldspar and quartz. It typically occurs in upper levels of a hydrothermal systems above the zone of phyllic alteration, and it is where the formation of silica minerals such as quartz and chalcedony occurs. For the paragenesis, we have potassic, phyllic, and argillic stage. The difference is that the potassic stage of paragenesis occurs at approximately 600 to 800 degrees Celsius, where there is a formation of K-felds and biotite. The phyllic stage occurs at approximately 400 to 600 degrees Celsius, where there is an alteration of quartz and cerisite and the deposition of sulfide minerals. And in argillic stage forms at lower temperature, the stage that occurs at lower temperature that is less than 400 degrees Celsius, where the formation of kaolinite and late sulfide occurs. For the zoning in porphyry-related deposits is where porphyry deposits exhibits distinct mineral zoning due to magmatic differentiation, hydrothermal fluid evolution, and temperature gradients. These zones form concent- concentrically around the intrusion, reflecting variations in pressure, temperature, and fluid chemistry. The core zone is typically characterized by stockwork veins and disseminated sulfides mainly in chalcopyrite and bornite. It is within potassic altered rocks rich in K-felds and biotite. This zone represents highest temperatures and metal concentration, often hosting the bulk of copper and gold mineralization. The next zone is the intermediate zone that features phyllic alteration and contains increasing amount of pyrite and reduced copper contents. This alteration results from hydrothermal fluids replacing the potassic core, indicating cooling and increased fluid interaction. Lastly is the border zone or the outer zone, which consists of prophylitic alteration marked by chlorite, epitote, and carbonate minerals. This low temperature zones forms where hydrothermal fluids interact with the surrounding host rock, carrying out minimal economic mineralization but serves as an indicator for mineral exploration. Aside from this, some porphyry systems develop supergene enrichment zones where weathering processes concentrate copper as secondary minerals like chalcocite. These zones enhance ore grades and are important for economic extractions. The zoning in porphyry-related deposits is controlled by magmatic evolution, hydrothermal fluid flow, and temperature variations. Common gangue minerals of skarn includes quartz, calcite, epidote, diopside, chlorite. In Grayson, we have quartz, cerussite, epidote, topaz, and fluorite. In pegmatitic contact, we have gangue minerals like quartz, muscovite, cerussite, albite, topaz, and in porphyry related, we have gangue minerals of quartz, chlorite, cerussite, epidote, and calcite. So, to summarize the structural controls of contact metasomatic deposits, in skarn we have faults, fractures, fold hinges, bedding planes, and contact zones. In grayson, we have cupulas, shear zones, joints, and breccia zones. In pegmatitic contact, we have fractures, shear zones, intrusive margins, and dikes and veins. And lastly, in porphyry related, we have radial or concentric fractures, fault zones, and brittle to ductile zones. On the summary of chemical controls, the chemical controls of skarn are CO2 degassing, iron silicate activity, and silicate rich enrichment. On the Grayson, we have fluorine, boron, and silica-rich fluids. In pegmatitic contact are the water-rich fluids, alkali chemistry, and in porphyry-related, we have sulfur fugacity, chloride complexing, and pH variation. In the summary of depositional textures in skarn, we have granuloblastic and porphyroblastic. In Grayson, we have granular, pseudomorphic, veinlet, and stockwork, graphic, and open space filling. In pegmatitic contact, we have graphic zone, euhedral crystal, perithetic, and fracture filling textures. And in porphyry related, we have stockwork, glaciated, disseminated, veinlet, and replacement textures. The wall rock alteration and summary in skarn we have prograde and retrograde. In grayson we have granization, silicification, and sericitation. And in pegmatitic contact we have albitization, phosphatization, lithium and boron enrichment, and in porphyry related we have potassic, phthalic, and argillic. For the exploration of potential of contact metasomatic deposit, we can use the geological indicators like inclusion-related alteration, where we can map prograde or retrograde skarn minerals like garnet, pyroxene, and epidote as indicators of mineralization. We can also look for the host rock composition where carbonate rocks adjacent to granitic intrusions will be our primary targets for skarn and tectite deposits. We can also use geophysical methods like magnetic surveys, gravity surveys, and IP surveys, where magnetic surveys can detect magnetite-rich skarns and tectites. The gravity surveys identifies or can identify dense or bearing zones, and the IP surveys are effective for sulfide-rich Grayson and porphyry-related deposits. We can also use geochemical techniques like soil and stream sediment sampling, where it detects anomalous concentrations of minerals. This is commonly observed in mining or the gold mining operations where kinukuha nila yung traces of golds in the stream or sa mga ilog na malapit. We can also use the fluid inclusion studies where it determines the temperature pressure conditions of ore formation. And lastly, we can use the drilling and core logging where systematic drilling along skarn zonation gradients to locate metal-rich zones, and petrographic and isotopic studies to trace hydrothermal fluid evolutions. Here are our references. Thank you for listening, and we are now open for questions and suggestions. We would like to hear your thoughts.